Okay guys, let's take a look at today's lesson. So what we're going to be working on today are applications of conics. We've been working on this unit for several days now. We're just going to kind of finish it out with some word problems. Yay! Alright, so I just have a couple of problems for us to look at. So the first one, we have a doorway is in the shape of a semi-ellipse. The doorway is 10 feet wide and 8 feet high. The equation that would describe the ellipse. Okay, well you know me, I'm going to have to draw some pictures. So here's our semi-ellipse. Says our doorway is 10 feet wide and 8 feet high. Okay. Alright, so I think we can see this distance would be 5 and that distance would be 8. So since it's an ellipse, the longest side is the major axis, so we'll just do it first. So we have y squared over 64 plus x squared over 25. Now that is the equation for a full ellipse. If you think about that graphically, the full ellipse would be wherever y was positive. So if there was some reason we needed to solve this equation and solve it for y, we could force the y's to be positive for this top half. We're really not going to worry about that. We're just going to use the equation as it is, as a full ellipse, and then just recognize if for some reason we might get a point down here which doesn't exist, we would know that that would be extraneous. It's just that doesn't exist. There really isn't a way to, unless we solve for y, to force this equation to only represent a half of an ellipse. So for convenience sake, we're just going to leave it as it is. So there's our equation for ellipse. It says, how high is the doorway? 2 feet from the center. Okay, so let's look at the doorway again. So I'm going to place this, we placed it as at 0, 0, right? Our vertex, or the center, is at 0, 0. And so we're looking at, this would be an x value of 0, 2 feet from the center. And I'm just going to go 2 feet. I'm going to go 2 this way. So we're really looking for this height. This is the, we want to know how high that is. It really is a y value, right? How high is it at 2? What we want to do is we want to simply substitute in a 2 into this for x. So I have y squared over 25 plus 2 squared over 25 equals 1. Let's start solving for y. Y squared over 25 equals 1 minus 4 over 25. So y squared over 25 equals, what is that, 21 over 25. Okay, let's cross multiply to solve for y. So we get 25 y squared equals 25 times 21. 25 times 21. And so we get y squared is 25 times 21, 13, 45 over 25. Okay. So when we were to solve this and square root both sides, we are going to get a plus minus answer. It's like plus minus 7.332. But we know that the negative y value would be the one for this bottom part of the ellipse, which really in our case doesn't exist. So that really isn't a viable answer, and we don't measure distances in negative anyway. So our height, it's 7.332 feet high. Okay, so that's the answer to that first one. All right. So let's take a look at the second one. We have 2 microphones 1 mile apart record an explosion. Microphone A receives the sound 2 seconds before microphone B. Where did the explosions occur? Assume sounds travel at 1100 feet per second. Okay. So this one is kind of strange. We don't really have an idea yet of what's going on, what kind of conic that would represent. let's kind of focus in on some information. We know that microphone A receives the sound 2 seconds before microphone B. So they receive the sound, they're different as a difference. That's a difference. Do we remember one of the conics with, as part of their definition, the word difference in there? Now, this is really talking about hyperbola. And let's go through. I'm gonna give you a saying. I'm gonna say what the rule is, and then I'm going to explain it, because just saying what the rule is and you don't understand what I'm talking about, you would try to memorize it, and that may not happen. So what the rule is that the differences of the distance, so the differences of the distance from any point on the hyperbola, to the two foci is equal to 2A units. A being what we normally talk about, A being is the distance between the center and a vertex of a hyperbola. Now you're like, oh great, what in the world is that? The difference of the distance from any point on the hyperbola to the two foci is equal to 2A units. Well, how does that even work? I just want to kind of show you a picture of how that works. Maybe that will help you kind of get that cemented in your memory. I want to make a little room over here on the other side so that I can draw this out, this concept. Okay, so let's draw a hyperbola. Just fairly simple. And I'm going to put the focus points right here and here. Okay, there's our focus points. And here's our vertices. Let's see what in the world we're talking about. So I'm actually going to, let's measure the distance. We're going to use this point right here. And we're going to take the difference of the distances between that point and the two focus points. We're going to do, and the point we know could be anywhere. Just for convenience, I'm using this point right here, and I'll show you why that's very helpful in just a minute. Okay, so we know the distance between here and here is A. Right, we know that. And we know that this full distance between the center and the focus is C. So if I'm going to be looking for this distance right here, okay, this is I'm going to measure the distance between the point and each focus and then subtract those distances. So this distance is what I'm interested in. That distance would be C minus A, right? That's what that distance would be. It would be C minus A. It says the difference of the distances from any point on the hyperbola to the two foci is equal to 2A units. Okay, any point to the two foci. So here's the distance from the point we're interested in to one of the focus points. Now let's calculate the distance between this point to the other focus point. So we want that distance. Okay, so we're going to look at this distance right here. So how do we come up with that distance? Well, okay, let's see. We know that this portion is C, right? A portion of that distance is C. Okay, that's good. We also know, I'll put that in red. So this is C. We also know that this distance from here to here, because we're trying to measure this whole distance in red, that's A. So this side is measured as C plus A. that a little easier to read. Okay, so it's measured as C plus A. All right, so what we're told is the difference between the distances. So C plus A, that's a bigger distance. So let's work on the formula, the difference. So C plus A minus, between the distances, minus our other distance is C minus A. So let's kind of combine like terms, C plus A minus C plus A. Those two drop away and we get, yes, amazingly, 2A. That's where this comes from, 2A. So we're going to use that piece of information in this problem. So let's draw out this problem. So it says the microphones are 1 mile apart, record an explosion. So being apart, a lot of students really want to make those microphones really bad. Okay, but that's not where they are. The microphones are at the focus points. That's microphone A, that's microphone B. And they are 1 mile apart. So this distance is 1 mile. Okay, so what they want us to do is, where did the explosion occur? Now, some students want an exact point where the explosion occurs. Really what this question is asking for is, what is the equation of the hyperbola? They want the equation of the hyperbola so they can, basically the explosion could occur anywhere along, we just said that this is true, no matter what point we're at, right? The difference in the distances is 2A. So anywhere, it could have been anywhere along these hyperbola pieces. So they just want the equation of the hyperbola. I mean, it's kind of a weird way to ask for the equation of the hyperbola, but that's what they're asking for. Just give us the equation of the hyperbola so that we can narrow down exactly where this explosion occurred. All right, so let's start using some of this information. We know that 2A is going to be equal to, what's the difference in they difference, they heard the sound 2 seconds, is 2 seconds. That's the difference in the distances. And we actually have a sound and distance an equation. So we know that sound travels at 1,100 feet per second. So we're going to actually be able to put this. I know it doesn't look like a distance. It looks like, time. But we're going to put a distance on this in just a moment. So 2A equals 2 seconds. That means that A is going to be 1 second. Now we need to translate that into distance, actual distance. And so if sound travels at 1,100 feet per second, then I know that A is going to be 1,100 feet. Right? If it's 1,100 feet per second, and it's 1 second, it's going to be A is 1,100 feet. Now, they're doing a little bit of a unit issue here. We've got miles and feet, and, we can't really have that going on. Let's go to feet. So 1 mile equals 5,280 feet. And so that's this distance right here. And what is this distance is also, so the distance between here and here is C, and here and here, see, this whole distance is 2C, isn't it? So really 2C equals 5,280. Why do we need to find the equation? We got A and we need B, but we don't have that yet. We do have C. So C is going to be 2,640 feet. All right, so let's use our little helper equation for hyperbolas. C squared, so 2,640 squared equals A squared, 1,100 squared plus B squared. So B squared is going to be 5,759,600. 5,9,600. That's what B squared is. So now we're ready to write our formula. So we have squared over our A squared 1,100 is 1,210,000 minus y squared over b squared, that was 57,59,600 equals 1. And there we go. This is every location where the explosion could have occurred. That, okay? And that is the lesson for today.